Hello, good morning. Am I audible?
Yes,
Good
sir.
morning, sir. Yes, sir.
Yeah.
Audible.
Okay. So today we'll discuss mazing problem. Okay. Uh, Yesterday you understood how to implement the circular queues using arrays. So now today mazing problem. So the problem statement is written here. So and this you have already played this game. It's a puzzle game. Consider a rat in a maze. So maze is nothing but a puzzle or which has multiple paths. Okay. So there is only one entry and one exit. Okay. The maze has got one entry and one exit. So the rat has to start from the entry that one entry what we have, and it has to reach the exit. Okay. And there are blocks in its path and can easily take wrong route. Okay. So when the rat starts at one entry and taking a path to reach the exit or the destination, so there are many blocks in its path, and so it can make the rat take easily the wrong path. So this problem is to find the correct path from entry to the exit, and this kind of puzzles are the games which you have already played. So in this problem, so the maze can be viewed as a two-dimensional array of ones and zeros. Okay. Now what we do, we are going to represent the maze as a 2D array which is filled with ones and zeros. And what one represent? One represents the path that can be followed, while 0 represents a block. That means, so the rat can go only in those direction wherever there is 1. If it is a 0, it is considered as a block. That means the rat cannot go there. So the various possible moves that can be made by the rat are, so the rat can go down, it can go forward, that is in the right side direction, it can move in the backward direction, that is in the left side direction, and even it can also go in the up direction. Okay. So these are the various possible moves that can be made by the rat. So in this process of finding the path, backtracking technique is used. So why backtracking we are saying? Say for example, the rat starts at some point and it finds that there is a 1 in the to the right side, and it moves there, and then again there is a 1 in the right side, it moves again to that block, say, and after it traverses like this 3 blocks and it finds a 0 and there is a block and it cannot travel further. Now what the rat has to do, it has to back travel. Okay. So it has to backtrack the same path what it has taken. Okay. And again come to its original path, find out which is the next route in order to reach the destination or the exit. So we make use of this backtracking technique. Hope the problem statement is clear.
Yes, sir.
Okay. So maze is represented as a 2D array which is filled with ones and zeros. 1 represents there is a path, and 0 represents there is a block. And the possible moves that can be made by the rat are, it can go down, it can go upward, it can go in the forward direction, it can come in the backward direction. And when the rat is traversing the maze, if it finds there is a block and further it cannot travel, so it can always backtrack and come to its original position and always look for a new path. Okay, I have the example here. Okay, so this is the maze now, which is represented as a 2D array. Okay, and all this is filled with zeros and ones right now. And remember that, so the entry, the top left corner is always entry. This is entry, and this should be always 1. And the bottom right corner is again 1, and this is the exit. Now so the rat will start from this position, and this way it cannot come, there is a block. Okay, and then the only option that is left for the rat to go is this way. So it comes this way, and again, so this way it cannot come, there is a block because 0 represents a block. and then it comes here. So this is the path, so which is taken by the rat in order to reach the destination. Okay, and this is also possible. Say for example, comes a multiple paths here, so the rat can take this path also. So it comes here, and again it can go down, come here, and something like this. Another one path is also there. It can come like this, it can come here. Now that's all. Only two possible paths are there. Okay, so this is the one which is already marked here is one path, or the other path is coming till here and then taking this path, okay, and reaching the exit. So like this, there can be multiple paths, but you have to find one such path. So hope you people understood.
Yes, sir.
Yes, sir.
Okay. So now the implementation of the same. Okay. So algorithm to find the path. So maze. So 0 to row. So this index, this is an array right now. So this value, this is the lower. This is one index, and this is the another index. Okay, because we say it is a two-dimensional array. Okay. Now this can vary from 0 to row -1, and this can vary from 0 to column -1, because we have these many rows here and these many columns. Now how many rows are there? 1, 2, 3, 4, 5, 6, 7. Okay, so since we are starting from 0, it is 7 minus 1. 0 to 7 minus 1, that is 0 to 6. And similarly, how many columns we have? So 1, 2, 3, 4, 5. Okay, 5 columns we have. Since it is starting from 0, it is 0 to 5 minus 1, 4. Okay, so this is what I am defining. And then row value, column value, the current row value and the current column value, and in which direction it has to move, whether it should move in the forward direction, backward direction, upward direction, or downward direction. Now initially what we are doing is I and j, we initialize them to 0, and then maze row comma column is equal to 1. Okay, so I'm checking initially if row comma, okay, maze of row comma column, if it is equal to 1, so the value at that particular location is 1. What does it mean? So 1 means there is a path. Okay, now I enter here. Now I have to store this path now, storing the row number and column number of the path. So I have one more array, path row and path column. Now there I store the row number and the column number using I and j. Okay, next what I do, so like this on every, so this is again a recursive function call. Every time this find path is called, I go for updating the row number and the column number if there is a 1, because it's a path. 1 means it represents there is a path, so that row number and column number is added to path row and path column. And after that I check whether I've reached the end of the column or end of the row. How do I check it? Like this: if column is equal to column -1 and row is equal to row -1, that means I've reached end of the row and end of the column. What is that? That is the exit point. So this point I have reached. It means I have reached this point. Now what I have to do? I have to go for printing the solution. Print the solution and go for printing all the paths which is stored in path row and path column. Okay, so I'm calling the function print now, which will go for printing the path, entire path that is stored in path row and path column. So this will display the row number and this will display the corresponding column number that should be taken in order to reach the exit point. Next, if this is not true, so in case if I have not reached the end of the column and end of the row, next what I have to do, moving from the last column. Okay, so I am checking whether I've reached the last column, something like this. Sorry, I'm checking whether I've reached the last column. Say first what I checked, I checked whether I've reached the exit point. So if I have not reached this point, then I go for checking whether I've reached the last column. So I may be still in the first row itself, but I might have reached the last column. Say for example I am here, so I am in first row and last column. Next what you have to do, so if that is the case, if you're in the last column, see if move is equal to down, okay, you got to move down. Say for example, I am here, I am in the first row and last column. Now where I have to go next? I have to come down, okay, because that means if I am in the first row, first column, this is the direction which I have traveled. Next I have to come down. So this is what happened. Move is equal to down. Now to move down, what is that I have to do? Same column, but I have to increment what? The row number, okay. So I was here, row number 1 and column number 5. Now I want to traverse downward, just have to increment the row number. So I just make row number as 2 and the column number still remains 5 itself. OP, people are following? Okay. So this is what I'm doing here. If maze of row plus 1 column equal to 0, that means block, there is no path. See, now when I try to move down, if this bit is right now 1, that means there exists a path. If this bit is 0, assume this bit is 0, I am trying to move down. So is it possible for me to move down if this bit is 0? Hello? Yeah, I cannot move down. Next, what I have to do? I have to backtrack. See, I have reached till here and I cannot move down. I have to backtrack. I have to go in the same in the reverse direction of the path which has traveled till now. What is that I have to do? And again I go for calling. When I try to move, if it is blocked, then again I call find path, maze I pass, row, column -1, okay, and then backward. See, same row number remains the same and column -1. I was here initially, I try to move to this position. So this, if I assume this is 0, this is blocking, I cannot move here, then I have to just backtrack, come to this position. To come back to this position, what will happen? Row number remains the same, only the column number you have to decrease by 1. So row number is still 1, the column number should be decreased by 1. That is what you are doing here. See, maze, row number is same, column is what? Column -1. Okay, people are following? And then move in what direction? Backward direction. Okay, the direction is set to backward, hence move backward. Hope you understood. Okay, next, and then, so this is for say if you're not moving, so same column, this one, move to next row, maze, row +1, same column, down. Say for example, here you backtracked here. Say for example, I want to move down here. If this bit is 1, I want to move down. So what is that I have to do? Column number remains the same. I have to just increment the row value and then I have to just move to the next row. Okay, so this, and then similarly, so here what we did, we checked whether we here using this if I checked whether I've reached the last row and last column. Now here I checked whether I've reached the last column. Next what I'm doing is I'm just checking whether I've reached the last row. Okay, something like this. So I've reached the last row. This is my last row. Okay, if row is equal to row -1, that means I've reached the last row, and move is equal to forward. What you have to do now? Row number remains the same, so column you have to increase. Say for example, I've reached the last row. Assume I have reached this row. Next what I have to do? I have to try to move in this direction. Okay, to move in this direction, so row number remains the same because I've already reached the last row. Only thing that you need to increase is the column number. That is what you're doing here. So maze of row, column +1 is equal to 0 if it is blocked. So I'm trying to move in this direction, trying to move in this direction. If this is blocked, say for example this is not 1 and it is 0, then what is that I have to do? I have to backtrack. I have to come back to this position. So I'm here, this way I cannot move. Next, what I have to do? I have to come to this position. I have to come back to this position and I have to check whether there is a path in this direction or not. Now for that, what we are doing, so if this is blocked, so again I'm calling recursively find path maze. Now what I'm doing, row minus 1, and the column number still remains the same. Why? See, this is row, say which row it is, 7th row. Now I have to just come here, 7th row, and what column? First column. So 6th row, first column it is, column number remains the same. Okay, so that is what we are doing here. Okay, so maze, row minus 1, column, and what is the direction in which we are moving now? Up. Okay, when I reach the end of the row, and if this is blocked, I have to move in this direction, up direction. So direction of movement is up. Okay, otherwise, so if move is not forward, so then I just if this is not blocked, say for example, so this is not 0, then I take the same row value, increment the column plus, and move in the forward direction. In this example now, so this is not 0, so if I am here, so I have the path, I can move here. Correct? No? Row number remains the same, I just increment the column, I come to this position. Okay, hope you are following. If I am in, yeah, understand. See, if I am in the last row, okay, if the next column is blocked for me, what is that I have to do? I have to move up. If I am in the last row and the next column is not blocked to me, I can move in the forward direction just by incrementing the column plus. Understood? Column by 1. Okay, else if next move is equal to backward. And what I am doing here, so if maze of row plus 1 column equal to 1, so moving down. Okay, so you call, so increase the row and column number remains the same because you are moving down. And similarly, else if maze of row column minus 1 is equal to 1, move in the backward direction. So else if maze of row minus 1 column equal to 1, move in the upward direction. Okay, next. So similarly for all other cases, because I've shown you here, with this you can easily trace all these things. So this is how the maze problem is implemented. So only thing is, you got to start from here and check in this direction. Okay, and check in this direction. Okay, so check if this is 0. If this is 0, that means this path is not available, you cannot move in this direction. So and then you have to traverse in this direction. So first I'll check this is 0, that means I cannot travel downward, I have to travel forward direction. I move here. Now when I am here, again I'll go for checking this. Okay, if this is 1, I'll move in this direction. If this is 0, and if this is 1, I'll come in this direction. Hope you people are following. So same process I repeat until I reach the end of the row or end of the column, or if I reach the end of the row, what I'll do, I'll try to move downward. Okay, downward by incrementing the column plus, by incrementing the row plus. If that is not possible, I'll try to backtrack. And similarly, if I've reached the end of the row, I'll try to move forward by increasing the column number, and if that is not possible, I'll try to backtrack. Okay, I try to move in this direction. In case if I've reached both this row end and also column end, then I go for displaying the solution. Hope you understood. Only 3 things are there. First thing is, you can move only in that direction where it is 1. When you are doing this, correct, no? When you are doing this, in case if you reach the end of the row, okay, you should try to move downward. Okay, in case if you reach the end of the row, so this is row, this is the first row. So in case if you reach the end of the column, you should try to move downward. In case if you reached end of the row, you should try to move forward. And if that is not possible, you should be backtracking by backtrack 1 position to the previous place, and then you have to see which is the next path that can be traveled. Okay, so in this process you should recursively keep doing until you reach both end of the row as well as end of the column. So this is the algorithm. Okay, so next what we have is multiple stacks. So you have understood single stack till now. So similarly you can have multiple stacks in a single array. So in the previous sessions and classes and all, we understood one array, one stack. So you created one array for storing elements of one stacks. But now what we do is, in a single array we can go for storing any number of stacks. Okay, and push and pop operation on each individual stack can be performed. Now how to do that? So it is demonstrated in this figure. You can observe this is one single array of size 15 created, 15. So 0 to 14 is 15. This is one single array, but how many stacks are implemented using this one single array? 4 stacks are implemented. So stack 1 of size 4, stack 2 of size 4, stack 3 of size 4, and stack 4 of size 4. Okay, so 0 to 14. So for totally 4 stacks are implemented here. So, and how many tops you should have? How many tops are required? Am I audible? How many tops are required? You require one top for each stack. Now in the one single array there are 4 stacks. For each stack you require a top 1, top 2, top 3, top 4. Okay, now each stack is one dimensional array and can be of any size but we have taken the size of each stack as equal here. So, and only one thing which has to be maintained, the total size of all the stacks should be less than or equal to the single dimension array. So this is what you have to. So the size of the stack can vary. The size of the stacks need not be the same. But one thing is, when you are creating the stacks of varying sizes within a single array, you should always see that the total size of all the stacks is either less than or equal to the single dimension array. Okay, next. Now let us perform the following operations on this stack. See, as already mentioned, so we need to maintain 4 tops now. So top 1 is the pointer to the first stack, and top 2 is the pointer to the second stack, top 3 is the pointer to the third stack, and top 4 is the pointer to the fourth stack. Say I want to perform this operation, push 10 in stack 4. Okay, now I make use of top 4 and then I perform the push operation. Observe here. So top initially, okay, yeah, now I make top to point to this beginning, and then 10 is inserted here, and then I want to push 20 in stack 3. Okay, see here, 20 is inserted. Okay, and after that 20 I have inserted 50 and 60 also, but the size of the stack 3 is not 4, it is only 3. You can just observe here, size of the stack 3 is only 3, of size 3, but the rest all are 4, because this is 0 to 14, size is 15. So that means one stack should have one less. Okay, so this is 4 plus 4 8, and this floor plus 4 12, 12 plus 3 is 15. Now, so pushing 20 onto the stack 3, and next push 30 in stack 1. See, top is pointing to this. Push 40 in stack 2. See, pushed. So push 50 in stack 3. So stack 3 we have already pushed 20. So top will be pointing to this position. Now we increment top, we make it to point to the 9, and we are inserting 50, and then push 60 in stack 3. So pushed. So now one single array of size 15 we have accommodated 4 stacks. Okay, so now here if you just look, so stack 3 is full and we cannot insert the element to the stack 3. So this is the stack 3 and it is full right now, and if I further try to push one more element to the stack 3 using top 3, it should say me stack 3 is full. Okay, So top 1, top 2, top 4 indicates the various top pointers for stack 1, stack 2 and stack 4 respectively. So this is also possible. Okay, next. Now indexes are important. See, top is here. Now when I take stack 1, the top should vary from 0 to 3. Okay, and after 3, when the top one reaches the index 3, and if I try to insert, it should tell me the stack 1 is full. And similarly, top 2, when it reaches 7, it should tell me the stack 2 is full. Okay, now, so stack 1, array of 0 will be the lower bound and array of 3 will be the upper bound. We have to set this. Okay, so that is, we can perform the stack operation. So perform stack 1 operations for the array of 0 to array of 3 only. Okay, that means I got to define the boundary of the stack 1. So array of 0 should be made as the lower boundary and array of 3 should be made as the upper boundary. And similarly for the stack, the area of the stack 2 will be from array of 4 to array of 3. So before when I declare a single array and I want to create 4 different stacks inside that, so the boundary of the stack should be clearly defined. So now similarly for stack 3, it is from array of 8 to array of 10. So array of 8 to array of 10. And similarly for stack 4, it is from array of 11 to array of 14. Okay, so thus you can declare any number of stacks having different sizes of them. So inside a single array, so you can create any number of stacks with a different sizes. Next, implementation. How do we implement the multiple stack? Okay, so here is the example now. So these are the header files that are included. Okay, max size of the array, I'm taking it as 20. I'm creating the array now as a global declaration in stack of max. Okay, and then now I told set stack function. Okay, so I have a set stack function, so using which I go for defining the lower boundary and upper boundary of the stack. Okay, so if I say index is equal to 1, so I make lower boundary as 1 and upper boundary as size of index. Okay. Else, if index is not 1, okay, what is this index? So we have to see the main program. Let me go to the main program. Okay, here. See here. So here, let me start from here. So I have these variables: n, index, I, item, choice, and then character answer, clear screen. If answer is equal to y, I'm initially assigning answer is yes. I'll tell you why this yes I am taking. Now for I is equal to 1, I less than max I plus plus. So I am initializing all the elements of my stack to minus 1. Okay, initialize the entire array of stack with minus 1, and then program for this is something program for multiple stack using single array, and then I'm asking how many stacks are required. Okay, so enter how many stacks are there or how many stacks are required. So I read into n the number of stacks. N is nothing but the number of stacks required, and enter the size of each stack. See, I'm reading the size of the stack here, each stack. For I is equal to 1, say for example I enter I need 4 stacks. Now you should be reading the size of each stack. I is equal to 1, I less than and I plus plus. So size of first stack, I read it. Okay, where I'm reading it? To size of I. Okay, size of I. And similarly I go for reading the size of all the stacks, and it is stored into the size array. Next what I do, I go for displaying this menu option. So as we did in the lab program, main menu, so push, pop, display, and so display displays 2 times display the specific stack, and display all is displaying the content of all the stacks. Okay, enter your choice. I am reading the choice. Next what I do, based on the choice, say for example I have taken the choice 1, I go to this, enter the item to be pushed. I am reading the item. After reading the item, immediately you got to read which stack. Okay, so which stack you have to insert. So I say insert it to the stack 1. Okay, so that is read to index. Okay, and then I'm checking, so st full of index, whether the stack 1 is full or not. I go to st full. Yeah, st full is here. Now I come here, so st full index is passed. What index is representing right now? The stack number, which stack. Okay, I assume it is first stack. So again I have the top, I and sum. Now set stack index, so this function I'm calling. Okay, now index is equal to 1. If it is the first stack, what will be the lower bound? 1. What will be the upper bound? Size of the index. Okay, size of the first stack, because size of the I have read already the size of each stack here. I'll show you. See, size of each stack is read and stored into the size array. Okay, what I'm doing, if it is the first stack, index is equal to 1, I make the lower bound as 1 and upper bound as size of index. If it is not 1, then what I do, sum is equal to 0, and I run a for loop for I is equal to 1, I less than index I plus plus, sum is equal to sum plus size of I. Because, so based on, say for example it is the fourth array, first I should take the size of first stack, add it to the sum, then I have to take the size of the second stack, add it to the sum. So then finally I get the lower index, lower bound of the fourth stack, and similarly the upper bound of the fourth stack. So lower bound of the fourth stack is sum plus 1, and upper bound of the fourth stack is sum plus size of index. So from there till the end. OP people understood till here? So it does something like that. Yeah, I'll write here. So this is one single array. Okay, so now say I want to create 4 stacks here. S1, let me say size 4. Okay, S2 size 3, and S3 of size 2, and S4 of size 2. Okay, now this S1 is from here to here, S2 is size 3 till here to here. This is S2, and S3 is 2. This is S3, and this is S4. Okay, for S1 what is the lower index? LB for S1 is equal to 1, and UB upper bound for S1 is equal to 1, 2, 3, 4, and similarly LB for lower bound for S2 is equal to 5, and upper bound for S2 is 5, 6, 7. So like this, similarly for S3 and S4. Okay, see, if I say what it is, let me come here. Yeah, see which stack I want to insert. Say I want to insert to the first stack, index value will be 1. Okay, now I am calling st full, so whether checking whether the first stack is full. So it calls this function, st full. Okay, index I'm passing. Now here I'm calling set stack index 1, so this function is called again. Now here I'm checking index is equal to 1. Yes, index is 1, so the lower bound for stack 1 is set to 1, and upper bound is size of index. What is the size of the first stack? 4, so upper bound is 4. OP people understood? Okay, now similarly, say for example I want to insert for stack 3, its lower bound is how much? 8, and upper bound for stack 3 is 8, 9. Observe now this. Now I want to insert for stack 3. Okay, so now you'll have to check whether stack 3 is full or not. It comes to this, index is 3 now. Now set stack index 3. This function is called index is 3. Now you're checking 3 is equal to 1. False it is. Comes to the else part. Sum is initialized to 0. Now for I is equal to 1, I less than index, I plus plus. Index is 3. Okay. Sum is equal to sum plus size of I. So size of first stack. What is the size of the first stack? 4. Yes or no? Hello? So size of first stack is 4. So new sum becomes how much? 4 now. New sum is 4. So initially this sum was 0. 0 plus 4. So new sum becomes 4. Now again go back. I value is 2. Okay. Now 2 is less than 3. Now size of 2. What is size of 2? Size of second stack 3. So this sum is 4. 4 plus 3. And new sum becomes how much now? 7. Okay. 7. Again go back. I becomes how much? 3. 3 less than 3. Condition is false. Come out. Now lower bound is equal to sum plus 1. What is the sum? 7. 7 plus 1 is 8. Which is, see, lower bound of 8 is how much? Lower bound of S3 is how much? 8. And you got it 8. And that is computed and assigned to LB. And similarly, you got to find the upper bound of S3. So UB is equal to sum plus size of index 3. Okay. So what is the size of this stack? 2 it is. Okay. So now yeah, 8 plus this is 8 plus 2, 10. Okay. I think this should be 10. Okay. No issues. No worries. Understood now? This is how it gets computed. So this function, set stack function, is responsible for setting the lower bound and higher bound of the stack. Is that clear? Okay. Now let me go back here. Okay. This is what I'm doing. Now here. Now which stack I select? I check whether that is full or not. Okay. So let me continue here. Okay, and after that, once the stack lower bound or upper bound is defined, now I make top is equal to LB and top less than or equal to upper bound, top plus plus, I do this. Okay, S of top is equal to minus 1 and then break. So if top minus 1 is equal to UB, return 1, else return 0. So if top minus 1 is equal to upper bound, what does it mean? The stack is full. Return 1, otherwise return 0. Okay, so stack full. If it returns 1, so stack is full. Do this. Stack so and so stack is full. You cannot push. Okay, else call push item. Okay. So this is the condition what you are checking here. If top minus 1 is equal to UB, upper bound, so then return 1, else return 0. Next, we'll go to push. So you're calling push item. We'll go to the function push. Yeah, push function is here. Again, only item you are passing. Now in top, so again top we are initializing it to the lower bound, and lower bound and higher bound are already computed. Lower bound and upper bound are computed here. Okay, using this function. Now check if stack of top is equal to minus 1, then break. Otherwise, you add the item to stack of top and then return. So this is how it gets added to the specified stack. Next, if it is case 2, Okay, say you want to delete, so again you got to ask from which stack, read the index, and now you are calling stack empty, passing the index. So you got to check whether the corresponding stack is empty or not. Okay, now we'll go to stempty. Yeah, stempty is here. Again set stack. Okay, now when you call this, the lower bound and upper bound of the stack is defined, and within that lower bound and upper bound I'm checking whether stack of top not equal to -1. If it is not equal to -1, what does it mean? Return 0. Stack is not empty. So if it is equal to -1, then stack is empty, return 1. Now based on this value returned here, okay, so if it returns 0, it comes to the else part. That means the stack is not empty. So pop an item and then say popped element is so and so, break. Okay, and then if the return value is -1, okay, so sorry 1, then we say the stack is empty. Next, case 3. So displaying from the specific task, mentioned task. Again you read from which task to display index. So display, so this is all, so display index. So again set stack, upper bound and lower bound based on the index. So then for top is equal to LB, top less than or equal to upper bound, so go for displaying, printing the elements. Okay, now when you call display all, okay, pass n is what? The number of stacks. I'll go to display all now. So in display all, now n is the number of stacks. So I take index initialized to 1 and index less than or equal to n. So I call for every stack, I call the set stack index. So this will define the lower bound and upper bound. Using that lower bound and upper bound, I print the contents of all the stacks. Okay, people understood? Okay, and here it's a default. If I don't give if I enter any other options apart from 1, 2, 3, 4, it comes to print exiting. So it comes to the default and it says exiting. And every time, so what we were doing in the previous programs and all, we used to make option 4. If you take option 4, it used to come to the option 4, and done you used to make it as 1 to terminate the execution of the program. Now here instead of that done, we are printing this. Do you wish to continue? And using getch read character from the keyboard. So if you wish to continue, either you should be typing lowercase y or uppercase y from the keyboard. So if it is lowercase y or uppercase y, it will allow you to continue further. So any other character apart from lowercase y or uppercase y, if you are reading from the keyboard, it will terminate the execution of the program. Understood now? Is that clear? Okay. So now output also is here, the sample run of the program. So how many stacks? 4 stacks we have told. Enter the size of each stack. Size of stack 1 I have set it to 3. Size of stack 2 to 4. Size of stack 3 to 5. Size of stack 4 to 8. And main menu is push pop, display all, and enter your choice. I am reading the choice as 1. Enter the item to be pushed 10. Now and it is asking me which stack to push. I have told 1, and it is asking, correct? No? So after doing this, and if I press enter, so the item 10 get pushed onto the stack 1. Now it is again asking me, do you want to continue? Okay, what I'll do, I have to either type y, small y, or uppercase y from the keyboard. If I type that, again you can see the menu option displayed for you. If you type any other character apart from y or uppercase lowercase y, so the program will terminate. Again I have the menu, and again it is asking me, enter the choice 1, enter the item to be pushed 20, which stack? 3rd stack. Okay, now again choice 1, 30, 3rd stack. Okay, and again choice 4 I am taking, display. Okay, all, see, stack number 1 I have inserted only one element. Stack number 2 I have not inserted anything. Stack number 3 I have inserted two things, 20 and 30. Stack number 4 not inserted anything. Do you wish to continue? And again it goes. Okay, understood now? See, if you know the implementation of single stack using an array, so then this can be easily done. Only thing is, single array you have multiple stacks. Okay, so anyhow this program is there, but you know the stack operations and all. So important thing here is that set stack index. So that is important, because that function is going to define the lower bound and upper bound of every stack. So if you understand that function, the rest all is easy. So now, two stacks in a single array. So you understood multiple stacks in a single array. Now two stacks in a single array. So I can have two stacks, something like this. See, this is one single array. So I make two arrays out of this. So two stacks out of this. So one stack will grow in this direction and another stack will grow in this direction. Okay. So for one stack, top value is initialized to 0. So for another stack, the top value is initialized to n minus 1. Okay, so for the stack to which this top is initialized to n minus 1 grows from right to left, and for the stack to which the top is initialized to 0, it grows from left to right. Hope people understood what I mean to say. Okay, see, one stack starts at the leftmost end. So it starts at the leftmost end and grows towards the right side. Okay, and other stack starts at the rightmost end and grows towards the left side. Okay, insertion in stack 1 moves top 1 to the right, while insertion to stack 2 moves the top 2 to the left. Okay, so this is one more way of implementing two arrays in a single array. Okay, so when stack is full, both top and top 2 positions are adjacent to each other. Okay, the advantage of this arrangement is that every location of the array can be utilized. So but here in this previous multiple arrays, what was happening, say for example we inserted it to stack 1, we inserted it to stack 3, two elements we have inserted, but stack 2 and stack 4 are still empty. Okay, now but this arrangement will efficiently make use of all the locations. Okay, so now the implementation routines. Yeah, now what I do now, so I initialize top to -1, so the pointer to the first stack which grows from left to right, and the stack which grows from right to left, I initialize it to n. Okay, so when I call push, observe here, so I am just checking what stack it is. So stack number 1 is nothing but the one which grows from left to right. Now, so before pushing, this is what I check. If top 1 plus 1 is equal to top 2, then what it is? The stack 1 is full. Following? So just observe here. See, so this has grown, top 2 has grown, and top 2 is here. Top 2 is pointing to this. Okay, this position. Now top 1 is here. Top 1 is here. That means all these locations are occupied. Top 1 is pointing to this. Now I want to insert one more by using top 1. What is that I'll do? See, and top 2 is here. What does it mean? All these locations are occupied. So top 1 is pointing to this, top 2 is pointing to this. Now if I try to insert one more to the stack 1, so top 1 plus 1, if it is equal to top 2, what does it mean? Stack is full. And similarly, now when I try to insert for top 2, okay, I want to insert to the top 2. So what is how do I check the full condition? Top 2 minus 1 is equal to top 1. OP people are following? So this top 2 value will be how much here? 5. Correct, right? I want to insert it to the this stack 2, which is growing from right to left. So top 2 is 5, 5 minus 1, okay, is 4, is equal to what? Top 1. So when you're inserting for the leftmost stack which grows from left to right, so how do you check for the full condition? Top plus 1 is equal to top 2. And similarly, how do you check for the full condition of the stack which is growing from right to left? So top 2 minus 1 is equal to top 1. So that is what we are doing here. So top 1 plus 1 is equal to top 2, stack is full. And similarly for the other one, if top 2 minus 1 is equal to top 1, the stack is full. Understood? And the rest all is same. Increment the top and go for adding the element. And when you are adding for the stack which grows from left to right, increment the top 1. When you are adding for the stack which grows from right to left, decrement top 2 and then go for adding. Hope you understood. Next, so when you are popping, okay, again, if you're trying to pop from the stack 1, how do you check for the empty condition? If top 1 is equal to minus 1, you say stack 1 is empty. And then, so assign the element pointed by the top 2 item, increment the top, return item. Similarly, if you are popping from the stack which is growing from left to right, now how do you check for empty? If top 2 is equal to max, it is empty. And then assign, and here you decrement top 2, here you increment top 1, because you want this to grow from left to right, and here you want this to grow from right to left. Hope you understood. One second. Oh, sorry, this is wrong here. Top 1, what is that you have to do? You got to decrement, and top 2, when you are popping, it has to be one second. This is growing like this, and this is growing like this. Top 2, yeah, this must be incremented. So I have written wrong here. Hope people can see this and understand. See, stack 1 will grow in this direction, correct? No? Yes or no? From right to left. Now, when you are popping, what should be done to the top 1? Decrement or increment? Decrement. So it is plus is wrong here. You have to decrement. And for the other stack 2, which is growing in this direction, okay. So this is from low to high, and this is again from high to low, okay. When you are deleting, so say for example here it is, so top 2 is here. So when you are deleting this item, what is that you have to do? You have to increment top 2. So this has to be incremented, this has to be decremented. Make a correction here. Is that clear? Understood now how to implement 2 stacks in one array by using 2 pointers, one growing from right to left, another going from left to right. Okay, so this is, and the next thing what we have is multiple queues. Similarly, you understood multiple stacks now. Similarly, you can also have multiple queues implemented within a single array, single one-dimensional array. Okay, so this will continue tomorrow, okay, from here. So this will take another 10 minutes to complete, and after that we can continue with the linked list. Okay, any doubts till here? Okay. So just be online until I finish taking attendance. Okay, 350 is there, 43 is there, 135 absent, 156 absent, 10 is there, 16 is there, 39 is there, 116 is there, 134 is also there. Okay. 135, 136, 137, 138, 140, 141, Shiv Shankar, 142, 143, 144, 145. Okay. 146, 147, 148, 149, 150, 151, 152, 153, 154. 154, 155, 156, 157, 158, 159, 160, 162, 164, 165, 166, 166, 167, 168, 169, 170, 171, 172, 174, 175, 176, 177, 178, 179, 179, 180, 181, 182, 183, 184, 185, 186, 188, 188 is there, 189 is also there, 190, 191, 192, 193. Okay. Okay, thank you. Yeah, thank you all.